Great. Okay, and then for the last talk, Oisín is going to tell us about small clocks which run by themselves.
Thank you very much for introducing me. I'll be talking about autonomous clocks in quantum electromechanics, the technical name for the presentation. But yeah, this is a project that I did with Mark, Michael, who I think is gone, and John Gould from Trinity, as well as Alessandro Silva. And brief apology for people who are in QTT in Vienna. This is a very similar talk, so yeah. And when I was preparing this talk, I kind of realized that a lot of concepts that I want to talk about have already been discussed in every talk, or not every talk, but a lot of talks since. So there's going to be a lot of repetition, I feel, in my talk.
Oh, we should debate about that.
Yeah. Yeah. But yeah, let's get started. So just a brief introduction on why we're interested in these kind of systems. So first of all, what is an autonomous clock? I know it's been defined before, but for my definition, it's just a clock that doesn't have any external degrees of freedom. It's kind of self-contained. There's no time dependence within the system. So this makes accounting in our clock easier and allows us to do this kind of analysis of accuracy, resolution, and dissipation of our clock. So to ensure that we're not cheating, essentially, to make a perfect clock when we don't have one. So in the macroscopic world, back in the beginning of the study of thermodynamics, clocks really didn't, the energetics clocks paled in comparison to the trains, the factories that they're producing. And not a lot of interest were put into the thermodynamics clocks. But as we kind of approach this more macroscopic world and as miniaturization takes place, these energetic considerations become more and more apparent. And of course, we should start to kind of understand, is there a fundamental limit to our ability to measure time to create a good clock? And this, I think, really started to generate steam in the past decade or so. So, for example, Ali's paper designing a toy model where he found that there is a kind of a trade-off between the accuracy of the clock as well as the dissipation of the clock. And this was then experimentally verified by Natalia Ares' group, who used this vibrating membrane and saw this similar trade-off. And then Michael's talk on Monday, where he described this experiment that they did in Australia with Jared and everyone down there. And then to talk about a bit of the more practical applications of being a good timekeeper, Jake's talk yesterday, where he discussed the fidelity of time-dependent control parameters when you have imperfect timekeeper. So with that, we kind of, what mark are we trying to make on this world? Well, we saw these really cool experiments by Natalia Ares' group. So this this experiment here that John Dexter in the back is an expert in. He had a poster on Tuesday, which I don't know if people here saw it. But this is a really cool experiment, and I'm just going to give a very simple explanation. Any technical questions, ask it. Basically what they had is a carbon nanotube that's snapped between two electrodes. And they can measure the position of this carbon nanotube via heterodyne detection. And what they see in this 2020 paper is that with a certain parameter regime, under high bias, they start to see these self-sustained oscillations occur in the system. And we thought, well, this is kind of cool. Why don't we try to make a toy model to explain this? So our simplified toy model, nowhere near as complicated as their system, consists of a resonant level model coupled to a harmonic oscillator. And the effect of this coupling is essentially when the electrons hop on and off this quantum dot, they'll kick this oscillator, which will in turn vary the energy levels of this quantum dot, which will then vary the current going through our system, which we want to measure and we want to make into a clock. So we can solve for the system in this quasi-adiabatic limit, where the electronic degrees of freedom relax much faster than the mechanical degrees of freedom. And with this quasi-adiabatic limit, we can do adiabatic elimination and generate this equation of motion for our system, which can then solve numerically and get these nice Wiener plots, as you can see here. And the really nice thing about this is that under a certain parameter regime, as we increase the bias from left to right, we start to see this Wigner function go from a thermal blob to this annulus shape, which signifies that we're storing work into this flywheel that hopefully, like in a future project, we can learn how to get it back out. But this is kind of a theoretical verification of what they saw in the experiment. So now for this next project, this new project that we're looking at, is we have this flywheel that's moving back and forth, which is changing the energy of this quantum dot. That means that the current through the quantum dot is going to, through the system is going to change. Can we measure this current to get sinusoidal output and make that into a quantum clock? So the questions we want to ask, is there a trade-off between the performance of the clock and the entropy production, similar to what's been done before? Will these self-sustained oscillations help us in creating a good clock? And how do we actually quantify the figure of merit of the clock? So first things first, how do we define the tick snare system? So to get an idea of what our clock is, we break it up into clockwork and register that Rob Silva has done before and many others. So our clockwork consists of just this electromechanical system that we discussed previously, whereas this register is this classical current that we're going to measure somehow and then post-process to get a tick record. So when we do that, we can calculate the current trajectories using a similar adiabatic elimination that we did perform for our oscillator. And we get these kind of current trajectories, which look quite noisy, but if you zoom in, you can see the sinusoidal nature of our current. And then we can define our ticks from this output. We've chosen the maxima of the current, and we can generate this ladder staircase function where we have parameter time and measure time on our clock. So the first thing we're going to do to look at the system is just look at the correlation function of the output. So what we can see here on the right-hand side, we have correlation functions, and as we go down, we're increasing the bias of the system. So what you can see is the correlation time increases as we increase the bias across the system, which would indicate that we're having improvement, we're improving the performance of our clock. What you might also see is that we have this kind of separation of timescales at higher biases. And now this took us a while to kind of understand what was going on. We're banging our head against the wall for weeks. But we designed these toy models to try to help us explain what's going on here. And basically this separation of timescale is just due to separation of timescale between our phase noise and our amplitude noise. And if you want more gory details, please take a look at the paper. But I'll spare you them for now. But from this, we can also find power spectrum. And as you'd expect, as we increase the bias across our system, the power spectrum amplitude increases, which just shows that we have a larger current going through our system. But also we can see this decrease in the full width at maximum, which means that our signal, our clock, is becoming better and better. But we want to use some of the tools that have been developed previously. So we're going to look at this waiting time distribution and the accuracy resolution. So the waiting time distribution, as Jared has mentioned in his talk, first talk of the conference, is probability distribution between consecutive ticks on our clock. So you can see here that these dots are numeric results for our ticks, and these solid lines are inverse Gaussian best fits. So this inverse Gaussian distribution, as had been said previously in the conference, arises from the first passage time of a biased random walk before it gets to a base of 2 pi. So this result was brilliant, that our numerical results matched this previous results that were known. So then we decided to look at the accuracy and resolution of our system. So again, as we discussed before in the conference, but a quick kind of reminder of what they are. The resolution is just the inverse of the average tick time, whereas the accuracy, to put it simply, is the number of ticks before your clock is out by a single tick. And what we can see is this trade-off between the entropy dissipated and the accuracy of our clock. So the accuracy increases as we increase the entropy to our system, which brilliant, the result that we kind of wanted to see. But these results really only apply to clocks that are a renewal process. So renewal processes are processes where after we detect a tick, the clock resets to its initial state. So our ticks will be then IID, and we can describe them using this weighted time distribution. So we decided to just probe to make sure that we have a renewal process by checking the relative entropy of our system. And as it turns out, this isn't a renewal process. So our system is a bit more complicated than systems that have been studied previously. So relative entropy compares this distribution of the multi-tick time distribution to a convolution of single tick time distributions. And for a renewal process, you'd expect two distributions to be identical, otherwise they'd be different and they'd show up as non-zero values in our relative entropy. And as you can see, as we increase the bias, this distance between our IID distribution and the one we actually got become more and more different. So to kind of probe this further, we decided to look at the mutual information between ticks that are n ticks apart. And again, we see this process where it's not zero. If this was a real process, these would all be zero, it would be happy, done. But you can see that for larger larger biases, this distribution becomes it's much longer lived. Yeah, so we need to kind of start to think about new kind of tools that we can use to describe the precision of these clocks. So one tool that's used in experimental research is this Allen variance. And Allen variance measures the frequency stability of a clock. So we decided to use that on our own system, so we can define this time deviation between our measure time and parameter time. And we can define this fractional frequency difference. And basically, for a better clock, we'd expect the Allen variance to be smaller. And we vary this as a function of the sampling time of our clock. So you can imagine if we sample our clock for a longer duration, we'd be integrating out more noise and we'd expect to have a better clock. So for the system, we can see that at low values of t, that the higher bias clock is much better. But as we increase t, we start to see this kink in the curve. And we believe that this kink is due to the loss of this temporal correlations that we've seen previously. So this timescale here matches up somewhat with the timescale that we've seen previously in mutual information. And once we lose this, we go back to our clock being a renewal process. So once we're at that scale, you can see that we have a scaling of 1 over tau, which is what you'd expect for a renewal process. So ultimately, we'd like to try to develop some more tools to describe these systems. But that's all that we had for this project. So just a quick summary of what we did in this project. We analyzed an autonomous clock that comprised of a nano-electromechanical system, and we looked at the trade-off between accuracy, resolution, and dissipation that's been done before. But also we looked at the presence of correlations between ticks. So our clock kind of goes beyond a lot of clocks that have been studied previously due to these correlations. Now there's more that we could analyze in this clock. For example, when defining the ticks, we didn't take into account shot noise that was present in the system, nor did we look at the amplification of noise that you need, or amplification of signal that you need to actually experimentally see the signal. Now what we want to do is we want to look at an experimental realization of this clock. So the guys in Oxford had this set up ready, so we're discussing how to actually perform this experiment. We also want to move away from this causative emphatic limit. It's quite limiting that in this kind of framework we have to stay there. But we want to move to a more stronger coupling regime between the dot and the oscillator. And we can do this by using mesoleads that Letizia had discussed yesterday, as well as tensor networks. And we want to see if we can extract a work from this oscillator that I mentioned previously. When we charge the oscillator, we can see how we do that, but we can't see how we can do the reverse and get out the work that we put in. And lastly, we want to understand more about these temporal correlations and how we can describe, how we can define the merit of costs in these systems. And with that, so once again, read the paper if you have time. And yeah, thank you very much.
I don't know why we're using the mic because there's no one online. But
Oh.
but I'm happy to come up. Yeah, true. Okay. Sorry. Yeah, I'm really intrigued by this temporal correlation stuff. So maybe a two-parter. Is temporal correlations a good thing? And do you have to pay entropy production for temporal correlations? And have you looked into it?
Temporal correlation, like the clients say they're a good thing, but I feel they could go either way. They could either hinder you or help you a lot. So it all depends on the system that you have. In our case, it looks like they help us due to this decrease in the Allen variance, but you could easily have another system where these correlations might hinder your ability to keep track. And the second question was again, sorry.
Do you have to pay more entropy production to have correlation?
I'm not sure, to be honest. It's a tricky question to answer. Not off the top of my head.
I'm happy to discuss it.
Yeah.
Ideas. Cool.
You mentioned briefly something about amplitude oscillations, amplitude noise in the first part of your talk. In the current simulations, I guess that's all the noise is involved. The amplitude oscillations on the resonator and the phase noise on the resonator all gets somehow or other involved in the current.
You gotta have this, there is a mix between the two types of noise.
Right.
But we develop kind of very simplistic models where you separate the two kinds of noise and you can see this separation time scale emerging.
You can.
Yeah, it is, yeah. Again, it's technical details in the paper, but it might be better to chat after.
All right. Thank you.
Anybody else? I actually had a question. There was something you showed, a slide you showed earlier on that I found kind of confusing. There was this autocorrelation function, or a temporal correlation function, which sort of looked like it had a logarithmic growth or something like this, was it?
This right here?
Yeah. Oh no. Yes, it wasn't very on time. Okay.
Information?
No, well that's what I was going to ask about the comparison between that. What was this correlation? This looked like a temporal correlation function about something.
This is the mutual information between.
It's a previous one, the autocorrelation function. Back one more. This one up here, on the top.
Oh, sorry. Yeah.
This, what is that?
This one, this one here. Yeah.
I mean, maybe I just totally misunderstood what you were doing with the slide. Can you?
So what we show in the paper is that we can divide the correlation function between kind of the stochastic or quantum part shot noise and this part that's due to the presence of the oscillator. So as the oscillator is moving back and forth, we have this current that's changing back and forth. And just naively, one of the first things that we did was just calculate this correlation function to see as we increase the bias, would this correlation function kind of become longer and longer lived? Or would it reduce, or would it stay the same? So,
Maybe a last short question, and maybe I missed it, but did you in the end compute the accuracy of that clock, in terms?
the accuracy, the accuracy we computed.
Okay, and so it's what kind of number?
It's massive. That is kind of the problem. Again, we need to. It's a problem that we've discussed before, that the accuracy is on the scale of 10 to the 4 compared to the entropy production. This could be due to a number of factors, such as not taking into the shock noise into account, not taking into the samplification into account, just the small nature of the current itself. It could be various reasons. Well, I mean, the point of this part is that we do see this trade-off as we increase the bias across the system. We do see an increase in the accuracy again, with these temporal correlations, the notion of accuracy kind of gets muddled up because of using derivation for the accuracy. You assume an IID distribution.
Okay. Okay. Yeah, I was just interested to compare this, I don't know, like, to an atomic clock. I just didn't have like some idea of like, oh, it's a very
We don't know when you're talking about.
Of course, but
But the L variance is actually more helpful.
okay.
Yeah, but I mean 10,006, good 6, right? So that's, yeah, a watch that goes off, goes out of time quite a lot, quite quickly within one day, right? Within an hour or two. So it's not a practical look. Yeah.
Still better than the thermal clock. I said one last question.
I'm just wondering, in your simulations, did you ever see things go beyond just millicycles to period Dublin bifurcations all the way through to chaotic dynamics?
What we do see sometimes in the rigor functions is sometimes we'll get caught like towards the center of the, or like above this threshold. That would get caught like at the center, like around origin, and then go back out again.
Oh, okay.
But this would be extremely rare event.
Okay. Oh, that's not part of that. That's some sort of biastability. I suppose.
Yeah.
Just sort of
Yeah.
switches off and then comes back on.
Yeah.
Okay.
Great. Oh, if there's no one else, then let's thank Oisín.